Hello everyone, and I am Showardopal. Today we are going to do result analysis and report generation of half dipole using HFSS. So we are going to find the following parameters using the HFSS software, and I will show you how you can generate your graph and report. I have already uh, created a PDF showing you that. So I already created a report, so I'm going to show you how you can generate yours by using the HFSS. The first thing is the antenna configuration and dimension, and in the HFSS I have opened, as you can see I have opened the antenna already, and this is the antenna. This is the half dipole antenna, and this is the whole structure. The outer thing is the radiation box. Okay, so for getting the antenna configuration dimension, what we are going to do is we are going to go to HFSS design properties, and here you can get the list of all the dimensions and parameters used in the design, and you can change the values from here also according to your design in your own model. So here you can see the dimensions are here, and you can take the screenshot of that portion and attach it in your report. For the finding the impedance, what we are going to do is the impedance that we have used in the excitation part. For that, what I'm going to do is go to the excitation part and click on this icon, and in the one click over here, and you can find you will be able to find the full port impedance that is being used in this case. You can change the impedance according to your need. This is arbitrary in this case, and you may change accordingly. So the first part is complete, and we are now going to plot the reflection coefficient uh, reflection coefficient uh, along the frequency. So for that, what we're going to do is go to the HFSS, come to the, okay, let's just doing some operation. Okay, they come to the result section, and for plotting the H1 which is also the reflection coefficient, what we're going to do is I have already created the result. This is as you can see, this is the dB plot of S11, which shows the reflection coefficient, and as you can see, this is the graph. And I'm show you how you can do you can also plot yours by going to results, then going to the model solution data report, rectangular plot. This is the rectangular plot, as you can see, and for that you can keep this thing. Say S11 is the parameter we need to choose, dB is the unit, and if I click new report, this report will be created. As I have already created the report, I'm not going to click on that. After creating, you will find this similar graph according to your model and frequency you have set already. As you can see, I have set the frequency from 1 to 3 gigahertz, and there is a cutoff at 51 the M1 marker, which is 2.19 gigahertz. And by using this graph also, you can find the cutoff and the bandwidth portions also. So this is the rectangular plot or the linear plot, and you can also see the S11 parameter of the reflection coefficient using the Smith chart. So as you can see, I have this Smith chart report, and by clicking on this, you will be able to see this is the Smith chart, and this diagram is same to this one, but the thing is that the Smith chart is in a different axis, and this first thing is in a different axis. Although it may look different, but it's actually basically plotting the same thing in different units and scaling. So for plotting the Smith chart, the process is very much similar. You need to go to create model solution data report, and you can choose Smith chart, and the thing is very much similar. As you can see, S parameter S11, and the function should be none. You may use dB. As I have not used dB over here, you can only plot the S11 and click on new report, and the data will be generated. As I already have that report, that's why I'm not going to generate that. The one thing that I want to show you is that the analysis frequency that we're using. As you can see, for the setup section, you can see that we are doing the solution for 2 gigahertz, and 2 gigahertz. Along with that, we are also doing a sweep up from 1 gigahertz to 3 gigahertz. As you can see, you can change these things from the analysis section in your model. So we have seen the S11 of the reflection coefficient parameter according with the respect to the frequency. After that, we are going to find the resonance frequency as I have shown in this list. So for the resonance frequency, as you can see, we can find the resonance frequency from the above graph, which is the S11 graph or the reflection coefficient. And if you look closely in the reflection coefficient, there is a dip in the frequency, and the reflection at this frequency is very much less, and this is the frequency at which the antenna will perform at its peak. So as you can see in this graph, 1 second. Yes, as you can see in this graph, I have the plot, and the dip shows that this is the frequency at which there is an antenna is resonating or best suited for. And there are other two graphs, there are other two markers at -10, and this shows the actually cutoff and the bandwidth you can calculate from this. So after viewing the resonance frequency from the above graph, we can calculate the upper and lower cutoff frequency from the above graph. As you can see, I have shown there are two other markers, M2 and M3. The M3 is the upper cutoff, and M1 is the resonant frequency, M2 is the lower cutoff. Yes, so I have written the values according to the graph I have shown above. You can calculate your values from your graph. So after that, we are going to calculate the antenna bandwidth. We can calculate the antenna bandwidth very simply by just subtracting the value of lower cutoff from the upper cutoff, and you can easily find the bandwidth. It is 0.52 gigahertz in this case for half dipole. Next, we are going to see the variation of real and imaginary part of the input port over the frequency. For that, what we're going to do is come to this section. As you can see, this is the plot of both the real part and the imaginary part of the Z11. Z1 is a parameter. You can also plot by going to the results, create model setter, rectangular plot. So this is as you can see, this is the Z part, Z11, and you can basically real imaginary part or the real part accordingly you can choose. As I have already have that plot, I am not going to click on the new report. If you click, you will have your report, and the graph will be similar to this one. So after finding this Z11 parameter, we can get the variation of real and imaginary part of the input port impedance over the frequency. So now we're going to find the radiation pattern in 2D, 3D or polar rectangular form. So in this diagram, you can see that this is the radiation pattern. So this is the radiation pattern. In this radiation pattern, what we have done is we have plotted the total gain with respect to different frequency. The frequency is 2.2 gigahertz in this graph, and we are varying the phi from one is 0 degree and one is 90 degree. In this case, you can also plot this thing, the gain. From the gain, you can plot from the radiation pattern. Yes, the far field report from the radiation pattern, you can plot that thing. You can plot the dB gain. For gain, you need to go to their gain total. There are many other gain also available. As of now, we are seeing this gain one, and there is geometry should be this, and dB should be selected as unit. And for varying the theta, there are two theta, 0 to 90 degree, or you can also set this. In this case is all, and you can also set the different values of theta like 0 and 90 degree according to your need. And this is the radiation pattern form of the theta gain. So this is a radiation pattern, and there is also another radiation pattern you can plot in the similar way. In this this radiation pattern, I have plotted the gain phi. In the previous case, I have plotted the gain total, and in this case I have plotted the gain phi. Yes, gain phi at various phi and gain theta. So this is the different color marking shows the different gain which I have plotted. So gain theta and gain phi at different phi angles. So these are just the radiation pattern form, and in the polar form, and I'm going to show how you can also plot this thing in the 3D. For 3D, here you can come over here. Yes, this is the 3D form of the theta at phi and other form. This is the spherical coordinate system, and you can also plot here by going to result, far field report, and going to 3D polar plot and a 3D rectangular plot. So 3D polar plot will give this thing, as you can see, and you can set the parameters. The graph will be very much similar to the one shown over here. The radiation pattern is shown is the gain total and the gain phi is shown in this part. So after that we are going to see the gain in the rectangular form. So for viewing the gain in the rectangular form, what we are going to do is come over here. Yes, and we have the gain total in the rectangular form. For viewing the rectangular form, you can go to far field report, rectangular plot, and just go to this gain total and click, and the different dB unit should be selected for this graph, and this the rectangular plot will be created, and click on new report after that. This is also very much similar graph of the gain, but it is just a little bit difficult. So it's a little bit different, and it is gain phi and gain theta at various phi. As I have shown in the 3D form, this is the thing in the rectangular form in this graph. Okay, so after plotting all these things, so what we are going to do is we are going to visualize the current or the electric field around the over the antenna. So for that, what we are going to do is come to over to field overlay. We will not be having these things, so I'm going to show you. So this is the model. So this is the model, and so after that, what I'm going to do is going to visit the so show you the surface current first. So for surface current, if I start calculating the values, just wait for me a few seconds, and we have the value. As you can see, this is the this shows the magnitude of the surface current at different position, and you can also plot that by going to this arm 1 and just going over here, plot fields electric J and J surface, magnitude of J surface. If you click this, the variation of the current, okay, the variation of the current at different points in the surface will be shown by the color map over shown over here. So this is the color form, and if you want to see the vector form, you can click on this. Okay, just yes. So this is the vector form. As you can see, this is the vector form. It is a little bit difficult to visualize, but this is the vector form, and the previous one is the magnitude form of the surface current. So after that, we are going to see the electric field distribution over the area space. So after that, I'm going to disable this plot visibility. After disabling this, we're going to see the electric field. So magnitude of E1 first. So wait for it to be for being calculated. So after being calculated, we will get the representation. Yes, as you can yes, as you have the graph. For generating this graph or the just representation, what you're going to do is click on this circle. As you can see, the whole circle is being selected, and if you just go to plot fields, electric and magnitude of electric field, then if you click this, then this graph you will get in your workspace. And I have already created the graph, and this is the one I have shown in this report. Also, you can take screenshot of the different reports and graphs and attach it to your report. So after that, what we are going to do is find the characteristic port impedance of the solution. So find the characteristic port impedance. What we're going to do is come to results, solution data. So after that, you need to click on Z0, and you will find the characteristic impedance to be a 73 ohm, and at the frequency it is calculated at. It is just so similar to the one shown over here. So after that, the radiated field is shown same as is shown in the electric field. This is the field being radiated from the antenna. And to view the vector form of the radiated field, what you need to do is just click on this and plot fields electric and vector D, not the magneto D. Electric vector D will show you the vectors at different point, as I am showing you in this case, that you can see. Disabling the visibility. So you can see the vector field have been plotted in front of you. This is very much similar to the one shown over here. You can also animate the thing over the various phases to visualize the propagation. So as you can see, I have animated the different phases of the vector field, and this is how the wave propagates along the space, and you can also do according to your need. So I am going to show you how this is the one shown over here. So this is the, as you can see, I have shown already all the things that you need to generate the report, and our task is complete. And you can see, you can also visualize the different components along the space according to your need, and you can also generate your reports if you need to. You can also visualize the magnetic field if you need along the space, and you can see how the radiation, the wave propagates along the direction. So this is all for this video, and you can also generate your report similarly like this. And thank you for watching till this end.